welcome to lecture 7. So, previously we learned the definition of derivative. We're going to explore that notion a little bit more, and we're going to talk about the function we obtain from a function that is differentiable everywhere inside an interval. Once we do that, the derivative itself is a new function which will contain information about the original function, and we'll start to learn about that relationship. But to begin with, let's continue with differentiability and get some clearer picture about it. So, given function f, which is differentiable, so differentiable from now on is just diff dot. We know that this means the following. It means that f of x minus f of a, x minus a, in the limit as x goes to a, will be this number f prime. So x goes to a, and this is f prime of a. Okay? And that limit doesn't necessarily exist, as we're going to see later, but if it does exist, then this is some particular number, and it's f prime of a, and that's what we learned last time. And of course, every time you see this, I want you to think of the picture. Here is the graph of our function. Here is a, f of a. Here is another point close by, x, f of x. And if we join these 2 points and then create a triangle like this, we see that the base of this triangle has got length x minus a, and this side length here has got length f of x minus f of a. So this quotient inside here is just how far up or down we go divided by how far along. And as we take x going towards a, we see it represents infinitesimal slope of the graph at this particular point. Note also that in this case I've drawn f of x is bigger than f of a, so when the derivative is positive, we're going to be increasing. If we have something sloping, if we have something where f of x is less than f of a, then this quotient will be negative, and that means the slope, negative slope means we're going downwards. Okay, so that's what we learned. Now let's examine this a little bit more closely. So, what does this mean? It means that f of x minus f of a over x minus a is very close to, so note this is not equals, this is approximately equal. This is very close to this particular number for x, which is very close to a, right? So let's multiply both sides by x minus a. So then we have is very close to. Okay, now I want to represent more closely what I mean by very close to in this case, because when I mean this number is very close to this number, I mean it's less than any particular thing that you want. That's the definition of limit. But when we multiply by x minus a is already a very small number. So this very close is very much smaller than this very close, right? Because this very close is whatever, less than 1 over a billion. This very close is less than 1 over a billion times x minus a. Yeah? Because we've multiplied the entire line by x minus a. So I'm going to try and represent that fact by writing this. I'm going to write plus minus little o of 1 and then x minus a. Little o of 1 is just a way to represent some small quantity that I don't want to define. It means it's much, much smaller than 1. And now when I write this, I'm going to actually put an equal sign rather than approximately equal. And all I've done here is I've just found a way to try and represent the fact that the difference between this and this is very small as a tiny, tiny fraction of this particular quantity, x minus a. And that'll be important going forward. Okay, so we have that. And now let's put the f of a on the other side. Let's do it over here. So that means that f of x is equal to x minus a, f prime of a plus f of a plus or minus little o1 x minus a. Good. Now, this part right here should seem somewhat familiar, right? If we write this, t of x is equal to x minus a, f prime of a plus f of a, what do we notice about this function? Well, it's a linear function, right? Because we just have, expand this out, it's just a constant times a plus another constant. So it's a linear function. And if we look at what the slope of this linear function is, it's given by f prime of a, which is the infinitesimal slope of the graph at a. And if we stick in a inside this, we just get f of a. So this linear function goes to the point a, f of a. In fact, this is exactly the tangent line, right? So this is exactly the tangent line. Okay? So let's examine what this says over here. It says that the difference between the tangent line, because this we've understood is the tangent line, and the actual function is a tiny, tiny fraction of x minus a. Okay, let's draw a circle around here of radius, let's say 2 times x minus a. Okay. I would normally blow this up, but I'm thinking that this picture is maybe big and is maybe good enough. Now let me blow it up. So if I blow this up to a bigger ball like this, what do I see? This is like the graph of our function. This is a f of a. Over here, well, more like over here, is x f of x. The tangent line is this line that goes like this. It was green last time, let's make it green. Well, whatever. We can deal with a change in color. And let's remind ourselves that the radius of this thing is of order 2x minus a. Yeah? So what this is saying, let's recall this is t of x, is that the tangent line given by this line right here and the actual function are small of some tiny fraction of the radius of this ball. Right? They are small compared to the radius of this ball. Yeah? And this is potentially a small ball, right? So the way I've drawn it here, it's not particularly small, but we could be doing this at a tiny, tiny little ball around here. When we blow it up, it looks like this. But the point is that this distance here is a tiny fraction of this x minus a, which itself is a very, very small thing. Yeah? Which means that when we look at this blown up picture, we see something that looks more and more like a flat line. So the graph of the function blown up to this screen of size 1 looks more and more like just a flat line given by the tangent line. Whereas, if we just took the graph of our function, so if we just took the graph of our function, and here is a f of a, and we just took any line going through it, it's still the case that locally around here, the line and the graph of the function get closer and closer together, right? So the difference between this line, this linear function, and the graph is small. But it's not small compared to the radius of the ball where this stuff is happening. If we blow up this ball, what do we see? If we blow this up to size 1, then this is the graph of our function, and this is the tangent line. it doesn't get any closer together as we get on a smaller and smaller scale. The blow-up picture looks kind of the same. It's not actually looking smaller on a scale compared to the scale which we're working on. Whereas this one actually is. That's encoded in the definition of differentiability. So, what's the consequences of that? That means that, as we'll learn going forward, that we can deal with relatively complex general things like differentiable functions by looking at them on a very small scale, because on a very small scale, they look a lot like linear functions. And that is one of the key ideas in calculus, and that's something we'll see going forward. So differentiability turns out to be extremely useful, principally because of that. It means that we can incredibly well locally approximate our function with a linear function. On a very small scale, this function looks like a linear function. It's also true here, because we can see this thing is differentiable, but we have to choose the right tangent line. Yeah? And there will be functions where it just isn't true. So if we have something like this, some kind of a kink, then there isn't any tangent line where we can fit it onto the graph. And when we blow up and blow up and blow up, it looks like it fits the graph better and better on a small scale with respect to the scale of the blow up. Right? That just isn't true. It's just, no matter how you blow this up, it's always going to look more or less like this. It's never going to get small. The error between the line and the graph is never going to get small compared to the radius of the ball. Whereas here it does. And again, it's because of this. It's because of this, because this is small compared to the radius of the ball, compared to the scale that we're looking at. Not just small, it's small compared to the radius of the ball. So, it is just what we learn from the definition. The math gives us this picture, tells us this is the meaning of differentiability. Okay? Cool. And that's the main thing you need to take away. Differentiability comes from this definition, that's the reasonable definition, and when we have that this limit actually exists, it means that the tangent line is incredibly well approximating the graph of the function. Incredibly well means that on a very small ball around the point we're approximating, the error is much less than the size of the ball. Okay, cool. All right, let us do some examples. Do not have much space. Let's start with this example. So consider and then sketch and its derivative and calculate and compare. Okay, so before we do that, let's just be precise in what we mean by something which is differentiable on an interval. So we say f is differentiable on an interval, say AB, if it is differentiable at every point on AB. We talked about this last time. And once that is true, then f prime itself forms a function. So f prime is a function on AB. So this guy is a polynomial, it's differentiable everywhere. So we differentiate it, we get a new function, and that new function is one we're going to sketch. And once we sketch that, we're going to do the calculation and see what the derivative actually looks like compared to what our sketching, our intuition actually told us. All right, coming up once I clean this board. Okay, so our function is this. And let's try and figure out what it looks like. So let's draw some axes. Now, as x increases, both x to the 3 and x are going to increase, but for very small x is going to be a lot bigger than x to the 3, right? If we have x is whatever, 1 over 4, then x to the power 3 is 1 over 64, right? A lot smaller than that. So initially, as we increase x, it's actually going to go down. And then when x equals 1, it's going to be 0, and then it's going to increase. So it's going to look like this. Okay? And it's also an odd function, which means that if we do this, we get this. So on the other side of the y-axis, it's going to be minus what we see on the right-hand side. So it's going to look like this. No? Cool. So let's try and understand the slope. So initially the slope is positive, right? Positive, positive, positive. This here is minus 1. This here is 1. And then somewhere between minus 1 and 0, the slope is 0. And then it starts to be negative, more and more negative. Maybe it's maximally negative around here. And then it's less negative, less negative, less negative. And then it's 0 somewhere here. And then it starts to increase slowly, and then it's increasing more and more and more, right? So once again, it's going to be, we expect something like this. It's positive to begin with, and then it decreases, 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 and somewhere between minus 1 and 0, it's actually hitting 0. And then somewhere around, well, it looks like around 0, it's probably at its negative, its most negative slope, so it's around minus something, maybe minus 1. And then it's going to be less negative, and it's going to cross and then go upwards, right? So it looks like a quadratic, looks like it's doing something like this. Just from looking at the slope, right? Nothing else is needed. Yep. So this is what we think f prime is, and the green is f itself. Now if we do the calculation, what happens? We go, the limit as h goes to 0 of f of x plus h minus f of x over h equals the limit h goes to 0 x plus h to the power 3 minus x plus h minus x to the 3 minus x over h. Expand that out. Limit as h goes to 0. We're going to lose the x to the 3, so we're going to have 3x squared h plus h to the 3. This minus x we cancel by this plus x, so we're just going to have a minus h, and that's all we're going to get from the top. And since h is going to 0, it's not actually 0, so we can cancel the h. This is the limit as h goes to 0 of 3x squared plus 3xh plus h squared minus 1. And then the limit as h goes to 0, this and this drops out, so it's just 3x squared minus 1, and that's it. That is our answer. And sure enough, that's a quadratic, right? So f prime of x equals 3x squared minus 1, and that's looking a lot like what we see. So when it's 0, this is the same as having x being plus or minus 1 over square root of 3, which is some number between plus or minus which is some number between 0 and 1 and between minus 1 and 0. So right here and right here is 1 over, oops. This is 1 over root 3, and this is minus 1 over root 3. Cool. So it's got the right shape. Sure enough, the maximal negative slope occurs at 0, and it's confirming the picture that we developed. And we get a bit more information. We actually know exactly where the derivative crosses 0. And this is the way I want you to do things. I want you to take this question and first visualize it. First, think what the function looks like and what you think the derivative looks like. And you should be able to do that, get a pretty good impression. Then you do some math, you do some calculation, you try and confirm your intuition, your visualization with the actual language. And we get through and we get this answer right here, and then we check back with the picture we've drawn. Sure enough, it completely confirms it, right? Do not do the other way around. Do not start to calculate and then get some answer and then think, okay, that's the answer. Don't think that this stuff, this algebra, this stuff is the actual business of what we're doing. This is just the language, the check. This is the thing that describes these pictures. We start with the pictures and we use this to augment and help us understand them, get a better understanding, more precise understanding, and to check that we're right. But the pictures are where we start from, not the symbols, not the algebra. Okay? But what is really cool, and we'll see this over and over again, is that if you have the right picture, then you exactly get it confirmed by the math. So you can do this kind of backwards and forwards from the picture to the language, to the math, and then back to the picture. And in every stage, you will be able to confirm the pictures in your head with the language, the calculation that you do here. As a research mathematician, that's exactly what I do all the time. I have some picture in my head, I try and express it in the language of math, I try and do the calculations, do the estimates to verify if the picture I think I have is correct. And often I'm correct, but often also I'm wrong because my intuition is a bit incorrect, I have a misunderstanding, and then the math I do will clarify it for me. The more you do this kind of thing, the more your intuition will learn the correct pictures. And the same actually in research, that the more I'm studying some question, the more my intuition, my pictures in my head is confirming what I see, is giving me the correct picture because the calculations I'm doing are teaching my intuition what is actually going on inside this situation. All right, so that is a solution to this question. Let's maybe do another one. Let's consider this example. F of x equals mod x. Where is this differentiable? And it's the same kind of game. So we're first going to try and understand this, visualize it. It's not particularly hard to visualize. We see it looks like this, right? It looks like this. And we know that being differentiable means that we can locally approximate the function incredibly well by a linear function, and that's absolutely true anywhere here and anywhere here. It completely fails to be true at 0, right? It doesn't matter what line we put through this, it's never going to approximate the function well. Yeah? So our guess, or our intuition, tells us it should be differentiable everywhere except 0, and at 0 it completely fails to be differentiable. And now we just confirm it. So if we do f of x, it's actually defined as follows. It's x if x is bigger than 0, and it's minus x if x is less than 0. So bigger than equal. Yeah? So sure enough, if x is bigger than 0, the limit as h goes to 0 of f of x plus h minus f of x over h is just equal to the limit as h goes to 0 of x plus h minus h over h, which is just the limit of h over h, which is just equal to 1, right? Easy. And if x is less than 0, the limit as h goes to 0, f of x plus h, f of x over h. Now, since x is less than 0, then this is the limit as h goes to 0 of minus x plus h, minus minus x, which is plus x over h. And now we're just going to have, this is just the limit as h goes to 0 of minus h over h, which is just minus 1, which again confirms with our picture. We see the slope is going to be 1 if x is positive and minus 1 if x is negative. Okay? And the reasoning which I did to begin with of that differentiability means we can approximate very well with a tangent line on a very small scale is enough to we could run the same argument to show that there's no differentiability at 0. Or we could do something else. So another argument to do that is that we see that if we try and take the definition of differentiability, but just taking h going to 0 from the right-hand side from positive numbers, then there will be a slope. It'll be plus 1. But if we take it from the left-hand side, there'll be a different slope, which is minus 1, which means if we take the definition of differentiability and we take h to 0 from different directions going towards 0, from the positive numbers and from the negative numbers, we get different answers, which means that there is no limit, right? Because if something has a limit, then it has a limit whether you approach from the left or the right, right? That's one of the things we learned. Something has a limit if and only if both one-sided limits exist and agree with each other. And that doesn't happen, so let's check that out. So it is not because the limit as h goes to 0 from the positive numbers of f of h minus f of 0 over h is just the limit as h goes to 0 of h over h, which is 1. And the limit as h goes to 0 from the negative numbers is the limit as h goes to 0 minus of minus h over h, which is just minus 1. So both these one-sided limits exist, but they do not agree, and therefore the limit as h goes to 0 of f of h as f of 0 does not exist. Cool. So that completely answers that question. And the same procedure. We drew the picture, we got a good understanding about what we should do and what's the case, and then we used this language, used the math to confirm it. All right. Let's talk about the different ways things can fail to be differentiable. Oops. So in this case, we already encountered one, and that's where you have this thing which, let's call it a corner, where clearly there's some kind of a kink or a corner in the graph, and there's no way you're going to fit a line and make a very good approximation locally at that point. So 1, corners. The second way is, or a second way, there's 3 ways, is it could be discontinuous. So I don't know how to spell discontinuous. That's right, discont. Discontinuities. And what we mean by that. So we've learned that it's differentiable means that the tangent line does incredibly good approximation, right? Locally around the point. If we have a function which has a break in the graph like this, then there's no tangent line that's going to approximate it very well, right? If we put a ball around this, then the graph of the function is not well approximated by this line. As we blow that up to a bigger and bigger scale, it's going to look like a half line, whereas the tangent line is a full line through, right? So this thing fails to be differentiable. What is perhaps less intuitive is that if we have a function like this, where it's perfectly nice, and then we just have a jump discontinuity at one point like this thing too, even if it's like flat, just like I've done it, this thing fails to be differentiable, because differentiability means that the tangent line's approximating it incredibly well on small scales, but for everything inside the ball. That's inside the definition, right? And if we look at this function inside the small ball, the tangent line is doing an incredibly good job of approximating the function except at the point itself, and there we don't have an approximation. So if you look back at the estimate we had that f of x was equal to the tangent line, t of x, plus or minus some small error, then x minus a, okay? And this was true for every single x, which was near a. So for all x near a, yeah, every single one. And it is not true for a itself, right? So when we stick a x equals a in this example, it is not the case that f of a is well approximated by the tangent line, because f of a is right up here, okay? So, for this thing, I mean, this, if you look back, is just the definition of differentiability, says that this kind of jump discontinuity means that we are not differentiable there, right? So discontinuities are indeed things which completely rule out differentiability. If it's discontinuous, then it can't be differentiable there. Okay, the third thing is vertical asymptotes. What do I mean by this? If we have a graph that does something like this, and we want to try and approximate it by a tangent line at 0, then we see that the only line that seems to do a reasonable job is just this vertical line like this. But this is not a tangent line. This is not a linear function, right? There is no function that we can define that gives us a vertical line. And such a function that has that kind of behavior isn't hard to define. So we could define f of x as follows, to be equal to the square root of x if x is bigger than or equal to 0, and minus the square root of minus x if x is less than 0. And that produces that kind of a shape, right? So the graphs of square root of x is one of these elementary graphs that I hope you'll get familiar with. It looks like this, because for very small x, the square root is actually a lot bigger than x itself. Yeah? So it's going to curl like this, and this thing is not differentiable. If we even try and just try and take the derivative and see what happens. If we do the limit as h goes to 0 of f of h minus f of 0 over h, then that's the limit as h goes to 0 of square root of h over h, right? And what's that? That's the limit as h goes to 0 of 1 over square root of h, which is blowing up equal to infinity, and therefore it doesn't exist. So it doesn't exist as a, because when we say it exists, we mean exist as a number. So something like that is not differentiable at that point. So that's what we mean by vertical asymptotes. So if you see any of these three behaviors, then you know for sure that your function is not differentiable. Okay, more coming up in a second. Okay, different notations. Oops. So Newton's notation for the derivative of a function is this thing, right? Sometimes you'll see this. And sometimes you'll see this. And they all mean exactly the same things. This is more like Leibniz notation. This is a kind of version of Leibniz notation. They're identical, so don't get hung up if you see these different things. They're completely identical things. Higher derivatives. So if we have a function which is differentiable, it could be that its derivative itself is differentiable. So if f is differentiable on some interval and f prime is differentiable then we can form the second derivative. Then we write f double prime of x, and that's the derivative of the derivative. Okay? Let's do an example. So we already considered this function f of x, which is x to the 3 minus x. If we differentiate this guy, f prime of x, we have 3x squared minus 1. And this itself is a perfectly good differentiable function. We've differentiated x squared before, which turns out to be 2x. So we can just write down that the second derivative is just 6x. Yeah? And let's see if that conforms with our picture. So we learned that the graph of f looks like this. We saw that the graph of the derivative looks like this. Yeah? Not very symmetrical, but you see what I'm trying to do. Yeah. And then let's look at the derivative. So the derivative is negative. So we're looking at the derivative of the derivative. So let me put these things in. So this is f prime, and this is f. And if we look at the slope of the derivative, then we see that it is negative, negative, less negative, less negative. It hits 0 here, and then it is positive, 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 right? And sure enough, when we look at the second derivative, we see it's equal to 6x, which is just this function like this. Just this straight line function, which is negative on the left-hand side and positive to the right-hand side. It's more negative the further to the left you go, which is what we see from this picture. Right? So the calculations and the pictures all fitting very nicely together. Okay, let's see what else. Okay, let's do another example of calculating the derivative. So, example. Calculate derivative of f of x equals the square root of x. Okay, solution. Let's get a picture of what we expect it to be. So we know that the graph of this thing looks, let's do it better than that. We know the graph of the square root kind of looks like this. Yeah, this is what f looks like. So it looks like, and we've already seen it, the derivative looks more and more steep as we get towards 0, and then gets less steep as we go off towards infinity, right? Because for very big numbers, the square root is less than x itself. So let's just do it. So let's look at this quotient. And when we see something like this, and we have these difference of two square roots, at this point you should be thinking this conjugate trick. Use the difference of two squares to kill the square roots. So we're going to do this. Like this, and we expand that out, and we're going to have x plus h minus x over h, and then x plus h. Okay, and the x is cancelled and the h is cancelled if h is non-zero, so we have this. Okay, so therefore the limit f prime of x, which is the limit h goes to 0 of this quotient, is the limit as h goes to 0 of this expression and sure enough that is just 1 over 2 square root of x, which you can write 1 over 2 x to the minus 1 over 2, which probably most of you know in any case. And let's check that it conforms to what we see. So, yep, it definitely does. So as we get closer and closer to 0, then the slope of the graph, the slope of the tangent is getting closer and closer to infinity, right? You can just see it like this, yeah? And as we get towards positive infinity with respect to x, then it flattens out and it flattens out and it flattens out. So this is confirming with our picture. And most of you who've studied calculus before know the so-called power rule for differentiation, and this is something you can verify. So as I've said before, it's very, very important that you guys know and are accountable and are clear about the definition of differentiability, know what it means. That's way more important than being able to actually calculate derivatives. And one of the ways we're going to test that, or traditionally we have tested that, is by asking you to differentiate from first principles a simple function like the square root of x. And you'll have to do this kind of stuff. You'll have to show you know the definition of differentiability and do the correct algebra to get to the answer. The advantage of this kind of question is that you know the answer anyway, so if you don't end up with the answer you expect, then there's some kind of algebraic problem. However, you have to actually do this stuff. If you just come up with this and then don't give a reason or claim the power rule or something, then it's going to be no point. We will say do it from first principles, which means do it from the very definition of differentiability itself. And if you ignore that, then you won't get the points. So practice this. Make sure you can do this. This is not hard. And practically any elementary function, we've done a number of examples now, you can push this through and get the answer you expect just from the definition of differentiability. Cool. So, in your WebAssign, you'll see questions like you'll have the graph of some function, and then you'll have the graphs of various potential derivatives. You're going to have to look at the function, look at the slope, and then just try and trace with your mind what the slope is going to be like if it's its own graph. Do it on a piece of paper a number of times, and then you'll just see that your brain will catch up and be able to do these pictures for you without you actually drawing it. That's another important skill you're going to have to learn, to identify what is the derivative of a function just from a bunch of different pictures. And it isn't particularly hard. You will pick it up fairly quick. That's the main things from this particular section. Going forward, we're going to learn how to differentiate some specific functions, and then we will just be able to use those rules. We'll learn how to differentiate polynomials, powers of x, elementary functions of other kind, so that we don't go through this anymore. So this is the last time we're going to do this for a while. But don't forget it, and make sure you can do it before we move on to different ways of getting out the answer. Okay, that's it for today. I will see you all, well, I'll see you, the Friday group on Friday.